Okay, so now that we understand the trends in effective nuclear charge across a period or down a group, let's talk about what effect effective nuclear charge, that was a lot of effect, has on the atomic radius. Okay, we'll deal with ions in a minute. Okay, so if your effective nuclear charge is increasing going across a period, well, that means those outer valence electrons are experiencing more of the positive nuclear charge. We know from electrostatics that opposite charges attract. So therefore, as the effective nuclear charge experienced by the electrons is increasing, those electrons are going to be experiencing more attraction to the nucleus, therefore they're going to be held in more tightly. So that is going to correspond to a decrease in atomic radius. If I can make this like fit in a nice box, I guess I'll just kind of scooch it up there. So the atomic radius, whatever. I think the comma is kind of moot if I move it down here. So atomic radius should be decreasing as you're going across a period, okay? So if we now look down a group, what would we expect to happen in the radius? Well, you're adding more stuff, right? You're adding more shells of electrons. So they're already further away from the nucleus. And because the effective nuclear charge is decreasing, because the amount of shielding is increasing, per electron, they're going to be experiencing less attraction to the nucleus. So they're already further away and they're also going to spread apart and be more diffuse, okay? So our atomic radius should definitely be increasing down a period. Sorry, down a group. But I wanted to go back to periods because if you think as well, because the electrons are going to be experiencing more effective nuclear charge, that is going to pull them in more tightly. So that's going to cause that decrease in radius. So they're like experiencing more charge like per electron. So thinking about like the charge per electron will help us understand what's going on with cations and anions. So remember, a cation is positively charged because it has lost one or more electrons compared to the atom that it comes from. So cations, it's lost something, is going to be smaller than the parent atom. Okay, makes sense. But we've also got to think about in terms of effective nuclear charge that it has more protons in the nucleus than electrons, right? So the effective nuclear charge per electron is increased. Okay, so that's actually more of a reason why the cations are smaller than the parent electron than just losing something and getting smaller, because obviously electron is minuscule, right? So it's more a case of the charge per electron. Each electron remaining, like if we take sodium, has Z of 11. So the sodium plus cation has got still Z of 11, so there's still 11 protons in the nucleus, but now there's only 10 electrons. So per electron, instead of feeling one nuclear charge, 10 divided by 11 would be what? Not 0.909090 recurring, right? 0.91 we'll call it. So then they are going to be pulled in more tightly. I've done that the wrong way around, right? 10 divided by 11. No, 11 divided by 10. They're experiencing 1.1 positive charges per. Why is my screen doing weird things? I don't know. Sorry about that. They're experiencing a greater than 1 positive charge per electron because there's one less electron to share it between. Okay. Same thing with anions. So anions are bigger than the parent atom. Okay, so you could think of that simply as like they've gained one or more electrons, therefore there's more stuff, they're bigger, but we know electrons are tiny. Okay, so what's going on there then? Why are they bigger? Because the number of protons now is less than the number of electrons, right? So take fluorine, for example, it's got 9 protons, 9 electrons, but the fluoride ion, F minus, has now got 10 electrons and only 9 protons. Okay, so that positive charge is of 9 plus 9 is split between 10 electrons, so they're only experiencing 0.9 positive charges per electron, so they're just going to spread out more. So the effective nuclear charge per electron decreases, so they get to spread out a bit more and like fluff up, right? Also electron repulsions are coming into play, so if you've got more electrons in the same kind of area, they're going to want to spread out and get as far away from each other as possible. Okay, so like that's how you can remember the rules with logic rather than just trying to memorize a fact like this gets bigger, this gets smaller. Remember why. Okay, so anions are bigger than atoms and cations are smaller than atoms. Okay, so now you can kind of reason this stuff out. So I would always pick the two things that are similar that you can compare them to each other, and then get your sort of master list. Okay, so for this I'm going to compare magnesium plus the cation with magnesium the atom. We know atoms are bigger than cations, so magnesium must be bigger than magnesium plus. Okay, so that's one fact that we know. All right, so compare magnesium and sodium. Okay, so they're both in period 3, same period. We know that as you go across a period, your effective nuclear charge is going to increase, therefore your radius is going to decrease. So we know that magnesium is going to be smaller than sodium. So however we want to write that, sodium's bigger than a magnesium, I guess. All right, so now we should be able to rearrange these two facts into a total order. Okay, in fact, you know what, I'll just put it in the actual box. So sodium is going to be the biggest, then magnesium, and then the magnesium cation, right? Just put those two things together to make one list. All right, so we've got sulfur, magnesium, and chlorine. So find them in the periodic table. Sulfur, magnesium, chlorine, they're all in the same period. We know that effective nuclear charge is going to increase across the period, so radius is going to decrease. So the smallest out of these will be chlorine, and the biggest will be magnesium. Okay, so magnesium, what was the other one? Sulfur, then chlorine. All right. Then finally, we've got calcium, magnesium 2 plus, and magnesium. So we know that magnesium is going to be bigger than magnesium 2 plus. Let's sort out calcium and magnesium. Calcium is a whole period lower than magnesium, so calcium has to be bigger than magnesium. So now we can rearrange this. That calcium will be bigger than magnesium, which in turn will be bigger than the magnesium cation. Okay, so I had a little look around because I wanted to find another example with an anion in it, and we can see this second one here has got fluorine, chlorine, and the chloride ion. So let's just make sure we're comfortable with where an anion would fit into the festivities. Okay, so we know that anions are bigger than the atom that they come from. Therefore, the chloride ion is bigger than chlorine. We can say that for a fact. And if we compare fluorine and chlorine, well, chlorine is further down the group than fluorine, so chlorine has to be bigger than fluorine. So now we can rearrange these. The chloride ion is going to be the biggest, then chlorine, and then fluorine. Okay, so that's how we would deal with if we had an anion in there as well.